So notice a single synapse with one neuron may be only able to change the membrane just a little. But if we get more neurons firing, we can get enough sodium to come in to get that neuron to go ahead and reach action potential. That's what summation means. We're summing the membrane, we're adding a little neurotransmitter, more neurotransmitter until we get more sodium in so we can get that postsynaptic neuron to fire. Because a single neuron firing and getting sodium to come into the next neuron often cannot raise, the graded potential is not enough. We can't get enough of a graded potential to get an action potential. Here's a neuron firing that hyperpolarized. We already hypothesized what would hyperpolarize, either letting potassium out or letting chloride in. Either one would make the membrane more negative. Just get to this point. So, excitatory, here we have one neuron, that green one, fires. Okay, the membrane repolarizes before it can ever get up to threshold. But if we get that one neuron to go faster, we can bring in enough sodium to reach threshold to get the postsynaptic neuron to fire. So that is summing in time, temporal summation. Or we can get more than one presynaptic neuron to fire. And so they both fire together, which brings in so much sodium that by the time we get to the axon hillock, we've reached threshold and we can get an action potential. So that's called summing in space. And more space is taken up with more presynaptic neurons, bringing in more sodium. And then, of course, if anybody hyperpolarizes the membrane, we don't get an action potential. Now, we do this all the time. It's part of homeostasis. In order to get the bicep to contract, excitatory, I had to inhibit the tricep. In order to get the tricep to contract, I had to inhibit the bicep. So that happens all the time. Inhibitory, excitatory is going on all the time. So there's from another book showing we get more than one presynaptic neuron firing. We can raise that neuron up to threshold and get it to fire. But if anybody is inhibitory and hyperpolarizes in their spot, the summation will be inhibitory and we won't get an action potential. Now, I think this is cool. This is a computer model in which they looked at a single dendrite and they looked at all the little spines on the dendrite. And then notice all the red, these are excitatory synaptic regions. This is where there is a neuron and a neuron and a neuron and a neuron, and all of these are going to depolarize. But once in a while there's a blue spot. These are inhibitory neurons. They're going to hyperpolarize, keep that neuron from firing. We also have it, the whole inhibitory excitatory thing. When you inhale because of excitatory neurons causing these muscles to contract. What makes you exhale is to inhibit the excitatory neurons. You block the excitatory neurons and everything just relaxes and air pushes in. So you're doing that continuously, about 10 to 12 times a minute. Alrighty. If a neurotransmitter binds to the receptor on the target cell and caused an excitatory response, what was that neurotransmitter doing? Get that away. Neurotransmitter binds to a receptor and causes an excitatory response. So what's the neurotransmitter doing? Ponder that. people that are still pondering. Switch to the water. Yay! Sodium was going into the cell and depolarizing the membrane, which is working our way toward an action potential, which is excitatory. We're going to have something contract, we're going to have something do something. This doesn't make any sense because there's not enough sodium inside to do anything. This one's going to hyperpolarize. Again, chloride is not really in the cell. And then potassium is already in the cell. Now we can alter the number of receptors on a neuron, on a postsynaptic membrane. And that's what's happening right now in this room at this very moment for the last month, 6 weeks, month and a half. You have been increasing the number of receptors in the postsynaptic neurons in your brain because you need them. And I was older when I went back to school. I had been out of nursing school for 5 years before I went back. And when I went back, it was a struggle. Oh God, learning was hard. But then, after a couple of semesters, it got easier. And it gets easier because we're adding more receptors for the neurotransmitter. The postsynaptic membrane is adding more receptors because now I'm using those neurons. I need to learn. And then the other thing that's going on in your brain, you're actually adding spines to your dendrites to increase the number of synapses because you need a faster, brighter brain. And that's going on in this class. And has been going on as you've been taking classes up to this point. That's why learning hurts sometimes. It's like growing pain. All right, let me just go ahead and talk a little bit about neurotransmitters. The only one I lecture on is acetylcholine. The rest of these are in your book. You still need to know them. But we need to talk about acetylcholine because it's the most common. It was discovered by, after every semester, I look up the German pronunciation, and I still can't seem to do it. I got auto, but anyone speak German? I think the diphthong means that I make that a long O, and then not a diphthong means that's a short I. So, Loa? Oh, I don't know. Auto. All right, he had dog open and was stimulating the vagus nerve, and it was slowing down the heartbeat. And while he was slowing down the heartbeat, he was washing the heart with saline. And then he took that saline and he went over to another dog that was opened, and he dumped that saline on that heart, and that heart slowed down. And so he said there was something coming out of the vagus nerve that was slowing down the heart rate, and he called it, cleverly enough, vagus stuff. Okay, again, my German, vagus stuff, I don't know. Now, he did win the Nobel Prize in 1936. This was worth about $400,000 at the time. He had to flee Austria, again, because the Nazis were annexing Austria at that time. And the only way the Nazis would let him leave is if they left his Nobel money behind, which he did willingly. So that brings us to acetylcholine. The first one identified, the best understood. We're going to see that it's released in a few different places. And now we have a new term for you, cholinergic neuron. So a cholinergic neuron releases acetylcholine. A cholinergic receptor binds to acetylcholine. Everything except for the word. Ooh, I should have left that other one there. That's okay. So a cholinergic neuron releases acetylcholine. A cholinergic receptor binds to acetylcholine. So what do you think about this one? What do you think a dopaminergic neuron is putting out? Dopamine. What do you think a serotonergic neuron is putting out? Serotonin. All right, now here's a tricky one. What do you think an adrenergic neuron is putting out? Adrenaline, the lay term for epinephrine, norepinephrine. And you'll see those more when we get chapter 9. All right, broken down by acetylcholinesterase. We're going to learn later where it's released. This is what you need to know for homework 7. It's all neurons that stimulate skeletal muscles. 2 kinds of receptors, muscarinic, nicotinic. All right, Alzheimer's. Already told you we keep acetylcholine in the synapse longer. Myasthenia gravis, we keep acetylcholine in the synapse longer. All right, the nicotinic, it opens with 2 acetylcholines. It's directly on the ion channel. So here is the sodium channel. So the receptor for acetylcholine on a nicotinic receptor is right there on the sodium channel. So it opens sodium channels right away. Versus muscarinic. Muscarinic uses the G protein coupled receptor. And it will either open potassium channels and hyperpolarize, or it will open sodium channels and depolarize. Depends on the tissue. When we get to chapter 9, we'll talk what those words, nicotinic and muscarinic, are referring to. Okay. Ooh, is your brain full? Mm-hmm. So let's go to lab, poke each other with hot sticks.